Okay, very good morning to all dignitaries and dear participants. On behalf of Electronics Engineering Department of IERT Prayagraj and entire fraternity of the Institute, I Jitan Kumar Shukla, Assistant Professor in Department of Electronics Engineering, welcome you all in the Faculty Development Program organized by the Department of Electronics Engineering IERT Prayagraj, sponsored by AICT Training and Learning Academy, ATAL, New Delhi. With great pride and honor, I am here to introduce to you the speaker of this session, Dr. Satyabrata Jit, sir, professor in the Department of Electronics Engineering, IIT BHU, Varanasi, India. Professor Satyabrata Jit, sir, earned his Bachelor of Engineering from IEST, that is India Institute of Engineering, Science and Technology, Sipur, Master of Technology from IIT Kanpur, and doctoral degree from IIT BHU, Varanasi. He has worked as lecturer at the Department of Electronics and Communication Engineering of GB Pant Institute of Engineering and Technology, Pauri Garhwal during 1995 to 1998. He joined the Department of Electronics Engineering, IIT BHU, Varanasi as a lecturer in April 1998, where he has been working as a professor since June 2010. Professor Jit sir has served as the Coordinator Director, Computer Center, BHU, from February 2012 to March 2014 and Head of Department of Electronics Engineering during April 2015 to May 2018. He has also served as a Chairperson, Senate Postgraduate Committee of the IIT BHU from 2013 to 14 and 14 to 15 academic session. He has also served as a member of Board of Governors of the HBTI Kanpur and UPTTI Kanpur for a period of 3 years each. Professor Jeet sir has supervised 29 PhD theses and supervising 6 ongoing PhD research scholars and more than 50 MTech theses. He has published more than 189 journal papers in various peer-reviewed international journals, including more than 69 IEEE publications. He also co-authored a textbook titled Milliman's Electronics Devices and Circuits, 4th edition, published by the McGraw-Hill Publishing Company, New Delhi, with Jacob Millman and Christos C. Halkias as co-authors. He is one of the editors of 3 books titled Advanced Optoelectronic Materials and Devices and Emerging Trends in Electronic and Photonic Devices and Systems, both published by the Milliman's Publisher India Limited, New Delhi, in 2008 and 2009 respectively, and Advances in Microelectronics and Photonics from Nova Science Publisher, New York, USA in 2012. He has also published an edited volume of titled 2D Nanoscale Heterostructured Material, published elsewhere in 2020. He has worked as one of the guest editors of special issues on narrow gap semiconductors and low dimensional structures for optoelectronic application of the Scientific World Journal in 2014. His present research interests include the modeling and simulation of nano-scale CMOS devices for gas sensing and optoelectronic application, solar cells, etc. Professor Jeet sir is recipient of Indian National Science Academy Visiting Fellow in 2006. He has worked as postdoctoral research fellow in Optoelectronic Laboratory, Georgia State University, Atlanta, USA. He has awarded the Boyce Fellowship of the Department of Science and Technology, Government of India for the year 2010 and 11 to carry out some advanced research in the Max Born Institute, Berlin, Germany during the September-December 2011. Professor Jeet sir is the fellow of IET UK, IETE India and Institute of Engineers India. He is a senior member of IEEE USA. At present, Professor Jeet sir is working as Associate Director of 2 journals, namely IET Micro and Nano Letters and Journal of Electronic Materials. He is also editor of IETE Journal of Research. Professor Jeet sir has completed 4 sponsored projects as a principal investigator and 2 projects as co-investigator. He is the reviewer of many reputed journals such as Nature Communications, Scientific Reports, Laser and Photonic Review, IEEE Transactions on electron devices, and many more. He has also served as expert members of the UGC and AICT as well NBA team. Now I request and welcome Professor Satyajit sir to come and enlighten us.
Okay, thank you, Jatin, for this lengthy introduction. So, so the topic that I have decided today, uh, sorry, just a minute, share. So, is it visible?
Yes, sir.
Okay, okay, that's fine. So basically, the topic that I am going to deliver today, so that is an evolution in semiconductor devices, particularly from the point contact diodes to nanoscale MOS transistors, a brief journey. So here, so the outline of the lectures that I have planned, so that is early research on semiconductor devices, and then the point contact rectifier, which was invented by Sir Jesse Booth, and then some history of transistors, uh, because you all know that in 2020 we have celebrated the 75 years of the invention of the transistor. So that is why the I'll try to mention some details of the history of the transistors, and then invention of the MOSFET transistor, and then invention of the IC, and introduction to the CMOS scaling, and then some non-conventional, that is MOSFETs. Now, you can remember that the past research in so-called semiconductor that was started in 1833, that is by Faraday. Just a minute. I'm just pointer. I'm just going to say here. Yeah. So that is considered the first research, although at that time there was no terminology like semiconductor. But, in this case, Faraday observed the temperature fluctuation of resistance in silver sulfide. So that is considered to be the beginning of research in semiconductors. Now, the another breakthrough that we observed that is in 1839 by Edmond Becquerel, and he first observed the photovoltaics in silver chloride coated platinum electrodes when it was immersed in aqueous nitric acid electrolyte solutions. So that was, just remember this thing, the photovoltaics, that means it was 1839, and when even the photoelectric effect was not discovered. Photoelectric effect that was discovered in 1905, even much before that, that is some effect of light and photovoltaics that was observed. Now, 1873, that is a remarkable development by W. Smith, who discovered the photoconductivity of selenium. Then, from the device point of view, the first, some disturbance, background disturbance is there. I don't know why. So, was reported by K.F. Brown in 1874. So that was the first solid-state point contact rectifier phenomena was observed by Brown in 1874. And then contemporarily, that is the next point contact diode that was reported by Sir J.C. Bose in 1900. So the another important effect. So these are very preliminary research that was done by Adams. W.J. Adams in 1876, along with his student R.E. Day at Cambridge. They also observed the photovoltaic effects in solid system that is using selenium. That is in 1876. So photovoltaic effect, it was Becquerel observed in 1839, and again in the form of a solar cell kinds of things, it was discovered by 1876 by Adams. Now, in 1883, that is C. Fritz, he was basically a electrician. He built the selenium solar cell. Why this research I have just put it here? Because you all know that that is the I mean the photoelectric effect was discovered by Einstein in 1905, but all these research were much before that, when actually theoretically no phenomenon, what is the phenomenon behind it, it was not very much clear, and even the concept of semiconductor was not there. Now, so the device point of view, that is rectification in crystal, it was observed by Brown in 1874. What he did, he used some metallic sulfides and of various pieces, and in this metallic sulfide, then by connecting the electrodes of the two sides of the metallic sulfides, then he observed that the current in one direction was more, and in the other direction it was less. So that was you can say one kind of rectifying characteristics, that is that we use for the diode. And we have seen that for a diode, what happens in the forward bias, the current is very large, and in reverse bias, current is very small. So this kinds of phenomena was first observed in metallic sulfides by J. Brown. With his words, I can mention, I would like to read out, that is, with a large quantity of natural and artificial metallic sulfides and greatly varying pieces, the most perfectly formed crystals that I could find, as well as core samples, I discovered that their resistance varied with the direction, intensity, and duration of the current. The differences amount up to 30% of the total amount. So what he did, prepared the crystals, metallic sulfide crystals of different size, different pieces of different sizes, and then he just connected the electrode uh, from two sides, and he just applied a supply voltage. And once he applied varying the voltage in one direction, he observed that his current was more, and once the polarity was changed of the supply, then the current was less. So that is one kind of rectifying nature that was first reported. This phenomenon was reported by Brown in 1874. Now, based on these things, that is the remarkable invention that took place uh, in 1900, that is by Sir J.C. Bose. So that is we considered as the point contact diode, and the diode was based on, so the preliminary structure that we have shown it here, what Sir J.C. Bose did it that, so it here it was galena. Galena means here it is shown, that is uh, lead sulfide, right? So in this lead sulfide, it was put it here. Now here it was in wear. So this portion were sharpened just like a needle, and this was inserted into that. Here the arrangement that I have shown it here. So the galena crystal was placed here, and this wear, that it was just touched and inserted into this one, right? And then by applying a potential between these two terminals, Sir J.C. Bose, he observed that is current in one direction was higher, and other direction was significantly less. So that is simply, in other words, we can say that he observed the IV characteristics to that of a Schottky diode of the present day's device. I mean, at that time the terminology was not there, so he just this is known as the point contact diode. So that is why That is, although there are a lot of arguments are there, but still, it is believed that uh, it is the J.C. Bose was the father of the, that is, diode. Semi solid state diode. So now, little bit historical things I would like to mention here. Now, in this Galena detector, the this device actually it was patented in 29th March 1904. It was filed in 1900, but patent was awarded in 1904, and this is a US patent number. And you will be surprised to know that this is the first patent awarded to any Asian, and not only that, it was the first patent on any semiconductor device, right? So now the little bit history is there. That is, at that time, that is, J.C. Bose actually he wrote a letter to Rabindranath Tagore, and he just informed him that, sir, I have developed an artificial eye, and this eye is capable to detect the object which is much more beyond our vision. That is, which our normal human eye that cannot detect. So Tagore was very much happy with this invention, and then the J.C. Bose asked the nomenclature of this device, and then Tagore suggested a name that is in these kinds of tejometer. Tejo particularly, this particularly means that tejo means tejas, a Sanskrit word that is powerful, and meter means just like a meter, voltmeter, etc. So the patent was also called, the device name was tejometer. In this patent, the name was used, this tejometer. So now, after this invention, then Jesse was demonstrated this operation, but he was not ready to file a patent. Then somehow Swami Vivekanand came to know about this remarkable discovery of Jesse Bose, and he then advised him, that is, to go for filing a patent. But Jesse Bose was not ready to file the patent because he was in this view that, that is, scientific research should not be confined in the form of patent. It should be open to all, so he was not ready for filing a patent. But somehow Vivekanand convinced him, and then he told that okay, he will be filing patent, but he will only sign, but he will not do anything. And then Vivekanand he appointed Sister Nivedita to look into it, and Sister Nivedita she then contacted Sarah Bull. She was or as the wife of a Senate member of US. So, and she was also a business woman. So, Sister Nivedita actually then she contacted to Sarabul, and Sarabul actually applied the patent on behalf of J.C. Bose, and the patent was awarded in 1904. So this patent was, you just see the total thing is just like a in the form of a human eye, and this portion that was a lens, and at this focal point of the lens here, this galena detector that was placed here, right? So that is basically the light, electromagnetic waves, and anything, once they are entered into this one. So this focal point, it was, they meet at this point. At this point, this detector was used, and this detector actually, when there was any kinds of, waves are penetrated into this one, there was a deflection in this galvanometer. So that was the objective of that one. So this device was used as an detector for the electromagnetic waves. So now, based on this invention, this point contact diode, it was such a, as we have already mentioned, that this was the first semiconductor device which was patented by J.C. Bose. Now, because of this invention, and J.C. Bose observed these two, three things that was very, very important to note. So he mentioned that is this crystal which are used that can be uh, made uh, different types, so which we call it as the p type and n type these two days. So that also Jesse was observed. So based on these things, that is Neville Mott, who was awarded Nobel Prize in 1977. He made a comment on this patent that the J.C. Bose was at least 60 years ahead of his time, and in fact, he had anticipated the existence of p-type and n-type semiconductors. Now, note that at that time, there was no concept of semiconductor in 1800, 1900. So, but at that time also he used these things. So that is why. So this is considered to be the first point contact diode is considered to be the first semiconductor device uh, in the semiconductor diode in the literature. So in this patent, that J.C. Bose, I just have taken from this patent, I am, I claim and desire to secure by letters patent is a coherer or detector of electrical disturbances, Hertzian waves, light waves, or other radiations comprising a pair of galena contacts. So that was the observation in this, that is patent. Now, in this case, now what you observe these things, simply we can say that is in his word, that is a coherer or detector of electrical disturbances, Hertzian waves, light waves, or other radiations comprising contacting pieces of sensitive substances having a characteristic scarf, giving the relation between an increasing electromagnetic force and resultant current passing through the sensitive substance, which is not straight but is either convex or concave to the axis of electromagnetic force, and in which the return curve with a decreasing electromagnetic force when taken slowly approximately coincides with the formula. So very simple way you can say that is it was the IV characteristics of that of a diode. In one directions of the, that is supply voltage, the current, once the supply voltage was increased, current was exponentially increased, and once the polarity was reversed, that is current was very, very small. Okay, so I mean, one side it was just like a convex shape, another one is concave shape. So, and in both cases, that is the current in one direction is very, very high, and other direction. And then he observed that is if we, while we are increasing the potential or voltage, now once we are decreasing it, then also it was following the same characteristics. Okay, so that was the first characteristics of a diode reported by Sir J.C. Bose. Now, only the thing is that he used the material that is galena, that is lead sulfide. So that was the first device in the history. Now, little bit a historical note. Now, in 1901, J.C. Bose wrote a letter to Rabindranath Tagore to inform his discovery of an artificial eye to detect objects beyond our normal vision using galena detector. Now, in this case, after this discovery, that is several industries. I mean, in that particular period, he was on a tour, and in this tour, that is, sorry, just a minute, actually. Hello, am I audible?
Yes, sir.
Okay. So he was on a tour in 1900, and during that particular period, that he was just demonstrating his discovery there at different European countries. So at that time, actually, once the industries came to know that, I mean, this great invention of Sir J.C. Bose, then several industries approached him, and they requested him, that is, please do not reveal. I mean, he wrote in this letter to Rabindranath Tagore that many industries are approaching him with the request that please do not reveal all your secrets, all the details of your experimentation. So there is money in it, and you can't imagine how much. So we will take out a patent. We will only take half the profit, but that will also give you tremendous amount of money with which you can further your research and take it ahead. What they told that is whatever you have discovered. I mean, all the I mean, several industries approached me and asked him that is don't reveal your discovery to others, and you are demonstrating here and there, but please don't elaborate these things to others and your experimental details. It is a huge discovery. You can earn a lot of profit out of these things if we file a patent. Okay, so we will file patent on your behalf, and half of that money we will take, and half of that we will give you, and this amount will be a huge amount that you can't even imagine. Then he also, at the end of this letter, he wrote that is, I am really shocked at the greed for money in Western society. If I ever fall into this trap, I will simply not be able to do even a part of what I intend to do. I do not have time to even say what I want to say. So I turned them away. So then what he considered that he, I mean, returned all the industries, and they refused, I mean, he simply refused the request of the industries. And but somehow, I told you the history of that one, it was patented by Jesse Bush with the help of Sarah Bull, and now rest of the things become the history. Now this point contact diode, that is was just like that one. It was a crystal, and here, so this is a metal which was inserted into these things, right? Now this diode was still in used in almost all the communication circuits, because it is a very very high speed diode. And the commercial, I mean, series, if you consider OS69, OS79, so these are the commercially available diodes which are used in all the radio detected circuits, television detected circuits, etc. Only little bit change has been taken place. So this crystal has been replaced. I mean, galena has been replaced by germanium crystal, right? And little bit technology has been changed. Here, in between these two terminals, a high voltage capacitor that is being charged, and momentarily a large current is passed through these things, and it is believed that this end moment portions of that, and it is a cat whisker wear. So the metal point that is being basically melted out here, and it becomes stick to it. And this S-shaped structure is taken because when the current will be flowing through this one, due to I square R loss, I mean, heat will be generated there, and due to thermal expansion, the it can be expanded into this side and that side, so the contact can remain, that is formed there. So this is the diode which is still are in use, but modern diode that we can consider, it is basically a metal and a semiconductor junction. So this device we considered today's, we normally know it as a Schottky diode kinds of things. Now in the same kinds of things, so these point contact diodes, so just consider here a little bit. So আমার বিজি আছে একটু. So now here in this case, disturb. Okay, so this point contact diode that we have used, as you consider that, Jeshibos used a galena, that is lead sulfide, and later on actually, but it was not. That was replaced by later on by germanium also, but by using this concept, that is Pickard, GW Pickard, that used the first to sell commercial silicon semiconductor device. Now here, Pickard in 1906, he replaced this galena by a silicon. So Germany was replaced much later, but here, that is silicon was used as this one, and he filed a patent uh, in August 10 perhaps in 1906. So that is another point contact diode. So which used clearly the concept of Sargesius, and this device that was completely commercialized. So these diodes, solid state diodes actually, that was commercialized, and silicon based point contact diode was discovered, that was by GW Pickard in 1906. Now, consequently, that is another theory that he came, that is Mott, Schottky Mott theory, we know. So the theory of correctly, so it was predicting that is point contact diode is some kinds of metal and semiconductor junction. Now to explain the behavior of the metal and semiconductor rectification theory, that is point contact diode, then one theory was given in 1939 by Neville Mott, uh, and the Mott theory was extended by Schottky to examine the current conduction in metal semiconductor junction. So basically, that was the Schottky junction theory. Schottky junction theory means basically metal semiconductor junction theory. So that was achieved in around 1939 and 1940s, with the help of Schottky Mott and Schottky both. Then the IV characteristics for the metal semiconductor junction, based on the thermionic emission of majority carriers, that was suggested by Hans Bethe in 1942. And this theory, this Schottky junction diode equation, what Bethe had suggested, it is still in use. We still use, that is this theory. Now, here, there is metal and semiconductor at this junction, and I have shown these things in the semiconductor, N-type semiconductor. If it is an N-type semiconductor, then here this should be the Schottky junction, metal semiconductor junction, and how the current, IV characteristics of the diode of this junction, that was given by, that is Bethe. हाँ थोड़ा हेलो हाँ बोलो अरे मैं एक लेक्चर में हूँ यार मेरा अभी इस टाइम नहीं है so so the IV characteristics of the metal semiconductor junction, it was given by Hans Bethe in 1942. Now here the Schottky junction, here is a metal and semiconductor. There are two types of junctions are formed. That is, one is Schottky junction, that is rectifying kinds of junction, and another one is ohmic junction. In ohmic junction, current will be flowing in both directions, and junction should behave just like a resistance. But in the Schottky junction, that it should behave just like a PN junction diode, right? So now, if the metal and if the N-type semiconductor is there, so then under what condition the Schottky junction or ohmic junction will be formed, that depends on the work function of the metal. Phi m is the work function of the metal, and phi s is the work function of the semiconductor. Now, if the work function of the metal is greater than the work function of the semiconductor, for N-type semiconductor, then a Schottky junction will be formed, and if it is vice versa, then the ohmic contact will be formed. And if the semiconductor is P-type, then phi m should be less than phi s, then only the Schottky junction will be formed. And here a barrier potential, that is Q phi Vn, and phi Vn should be equal to phi m minus xi s. Phi m is the work function of the metal, and xi s is the electron affinity of the semiconductor. Right? So now here the basic phenomena which was explained here by Schottky and Mott also, that is due to thermal emissions, the electrons from the metal, so it cannot move in this side because there is a barrier. So until unless the electrons gains an energy equal to or higher than the q pi bn, the electrons cannot be moved, moved from metal to semiconductor side, right? But in the semiconductor side, this one here, the electrons now from this one, so this one, difference between this and this. So this is the built-in potential, just like PN junction. So this built-in potential can be reduced by applying a bias voltage, and as a result, the electron can easily move from semiconductor side to the metal side due to thermionic emission. Right. So this theory, that is metal semiconductor junction, that was I mean. Uh, established in around 1942 completely. So the rectifying nature or point contact diode characteristics, that is well explained by using this theory. Now these are some of the devices. Now the next remarkable kinds of invention which took place, that is the field effect transistor. Now, field effect transistor, that is Lilienfeld, he filed a patent in 1925. Patent was filed in Canada in October 22, 1925, and the patent was granted. And later also, it was again 1 year later, it was the same patent was filed in US, and the US patent was granted in 1930. So this patent number is this one. So he just proposed, although this is a simplified structure, actual structure I will show you. So he just gave the structure similar to that one. So it was a cuprous sulfide. So if we use that is two electrodes here and there, right? And it is a semiconductor, I mean, it is a another electrode. So what he predicted, that the current between the source and drain, these two terminals, that can be controlled by applying a potential at the gate voltage terminal. Hello, am I audible?
Yes, sir.
Okay. So that was proposed by Lilienfeld in 1925, and the actual patent device was here. So this patent was filed in October 8, 1926. So I mean that was in the Canada, sorry, in the US. But originally it was the first Canadian patent was filed on October 22, 1925. So first it was patent was filed in Canada, and later the same thing was filed in the US in October 8, 1926, and this was the patent number. So here I mean, this device here it was a glass, and here that is one electrode metal was deposited here. Ah, so that is another metal was deposited here, and this is another metal was deposited here, and then over this one cuprous sulfide was deposited in this way. So basically that was one terminal, that is gate terminal, and these two, the lower two, was considered to be the source and drain connections. But however, unfortunately, that is this device was never being fabricated. Even I mean, Lilienfeld also tried to implement these things, but he failed to fabricate and demonstrate this. It was completely theoretical perception, but there was no experimental verification of this device. Now, in early 1930, Oscar Hill, he also, that is gave the concept of a junction field effect transistor, and he filed a patent. And this patent, Oscar Hill in 1935, patent was awarded. It was a British patent with this number. What he did, the basic structure was here. So that is one electrode, this was one electrode here, and that was a semiconductor here. That is again completely theoretical. Then he considered that by applying this voltage here, that is whatever IV current, I mean current was detected by this ammeter. Now he considered that that is if a voltage with respect to this terminal is applied here, this terminal, maybe positive voltage or negative voltage, then that potential, that voltage with respect to this plate, this one. So if an electric field is created in between, then I mean this plate and this one. So then he predicted that that is this electric field will affect the current flowing in these two terminals. So that is also is considered to be one of the, I mean, preliminary idea that. But in both the cases, Lilienfeld and Oscar Hill, they gave the one concept is very much clear that that is using a third terminal, and the potential of this third terminal can be used to control the current of this two terminal device between source and drain. Okay, but neither Lilienfeld nor Oscar Hell were able to construct a working field effect transistor. So these were merely theoretical, that is patent. No, I mean theoretical they justified, but they could not explain experimentally. Now, in this way, the Bell Laboratory actually the research was, I mean, going on. That is to develop this three-terminal device, because two-terminal device was already demonstrated. It was successfully used by Marconi and many other electronic circuits. This point contact diode, but uh, they were in the process of developing a three-terminal device, that is transistor. Now, in this case, that is this John Barden, Walter Bratton, and Shockley. So there in the Bell Laboratory, actually, the Shockley was the group leader, and these two, Barden and Bratton, they were working under, I mean, Shockley. So in 1947, you all know that they developed, that is this transistor. So this transistor was demonstrated by these two great I mean, researchers, and Shockley was not involved in that. So in 1947, that is, they called the press conference, Barton and Britain, and they considered that they have developed the first, I mean, three-terminal device, which he named as the point contact transistor. What he did here, so this is the first structure of the transistor that was reported by Barton and Britain, not Shockley, right? So what it did here, I mean, this was a germanium crystal. In this germanium, I mean, this entire thing was germanium crystal. So in this germanium crystal here, that is one, that is gold foil was connected to it, and another gold foil was connected to it, right? And entire thing was on a metallic base. So this was a metallic base. On that one germanium crystal was placed. On this germanium crystal, an entire thing was in a hanging by a spring, and on this germanium crystal, that is two, that is metallic contacts that was made of the gold, right? So that is why, by using the concept of that of this Jesse Bose, so they just inserted into it. This another contact was inserted in it. So that is why that is one point contact was here, and that is another point contact was here, right? So this is the, and this is the metallic base. So what he considered that with respect to the base, if they apply, that is a voltage, that is this emitter and base, and then the collector current that was achieved, and they predicted that this device can be, and the current can be controlled of these two terminals by controlling the base current. So now, after that, now here a little bit historical things that I would like to mention here. So basic structure, if you just consider the point contact transistor, it was just like that. It was a, I mean, Later it was modified here. So you can consider it was a plastic vase is here. So in this vase here, two gold foils. Here these two gold foils, and these two gold foils. In between these two, there was a very tiny gap, very small gap was there, and this end was sharpened. And this was a germanium crystal, and both were that is inserted in on this crystal, and this was a metallic contact. And the entire thing was it is hanging condition, right? So this one, this metallic base was used as the, I mean, base terminal, right? And one, this gold foil was considered as the collector, and another was as the, that is emitter. That was the basic structure of the point contact transistor. Now on 15th December 1947, now here, that is when the point contacts that observed, that is here Breton, that is he just in the working notebook of the Bell Laboratory, he just mentioned that when the points were very close together, got voltage amplification about 2, but not power amplification. This voltage amplification was independent of frequency 10 to, I mean 10 kilohertz. That means here they observe, Burton, he observed that on 15th December 1947, that when, I mean, these two contacts were placed very close to each other, they obtained a voltage amplification of 2, but they did not get any power amplification. And they further observed that the amplification was almost independent, that is for the low frequencies, in the sense 10 to 10 hertz to 1000 10 kilohertz, that is amplification was almost independent of the frequency. Now, the another report, that is on 16th December 1947, he just noted another thing. The separation between points was about uh, 4 into 10 to the minus 3 centimeter. That tiny gap that we have considered here, so that gap was around 4 into 10 to the minus 3 centimeter. One point was used as a grid and other point as a plate. So, I mean, this point and these 2 points, one was used as a grid, another one as a plate. The bias DC on the grid had to be positive to get amplification. Then he observed that power gain 1.3, voltage gain 15 on a period bias of above 15 volts. So that was reported that on December 16, 1947, they observed that is both the power gain and as well as voltage gain. So that that is on the basis of the entry of laboratory notebook made by that is Breton. So now here the history is that, I mean, then Burton and Moore demonstrated the PNP point contact germanium transistor as a speech amplifier with a power gain. So, and that is why, that is 23rd December 1947. So that is entire thing, it was demonstrated on 23rd December 1947. Burton and Moore, that he demonstrated the by the speech signal amplification by using this, that is point contact transistor. So that is why we celebrate the birthday of the transistor as 23rd December 1947. So the that is worldwide we celebrate 23rd December 1947 as the birthday of transistor. Now, although these three persons were given the Nobel Prize for this discovery of the transistor, but actually there are 12 people who are directly involved in the invention of this point contact transistor. So that I have taken, that is W.S. Gotton, Genesis of the Transistors, so written in December 1949, and here he clearly mentioned that although these three persons were given the credit for the invention of the transistor, but actually 12 persons were directly involved in this one. So this is the point contact transistor that is being that is 50 years of celebration that was kept in the Bell laboratory. So this transistor, uh, but here I'd like to mention here that that is although the transistor that was discovered there, but Bell Laboratory did not make any public announcement that is before June 1948. Okay, so birthday is celebrated of the transistor as 23rd December 1947, but that is 1940, I mean, till June 1948, I mean, it was no announcement was made by the Bell Laboratory. So now here, just a sad thing that we have not mentioned so far, that in this point contact transistor discovery, actually Shockley was not at all involved. Even he was the group leader, but the Barden and Breton, they were experimentalists. They developed and demonstrated everything on their own and by bypassing Shockley. And with this incident, actually, that is Shockley was very much depressed, and because he was the group leader, but I mean he was not consulted with, so that is why uh, he was very much shocked uh, with the behavior of Barton and Breton. But at that time, he also realized one thing. He realized that the transistor which has been proposed by this complicated structure, like this structure, there is no industry will take it because for mass production, it is very, very difficult and this transistor will not survive. So he thought for an alternate arrangement or alternate structure for the transistor. Now, in this process, he filed a patent on September 24, 1948, and this patent number, this one, and he just gave the concept that if this is a PN junction, I mean N-type semiconductor and P-type semiconductor, and if this junction that is another electrode is placed just close to this junction, and if the current or if the potential is changed between these two terminal, and then the current between these two terminals, that is these two terminals, that can be controlled by applying, that is controlling the current of this one. So it was again a theoretical study, so he just predicted the structure like that one. So that you can consider it is the preliminary concept of the, that is BJT, that was proposed by Shockley. Now in the same process, then he came out with a different structure. So different structures he just predicted, several structures this predicted, and he filed a patent in June 26, 1948. And the patent was awarded this one on September 25, 1951, and he came out this structure that was the modern days, that is transistor structure. What is suggested, this is a N-type semiconductor, here also N-type semiconductor, and it is a P-type semiconductor, right? And then it was also again completely theoretical. He just considered that that is such a structure would be useful, and if you bias in this way, then he just considered that it can be used as an, that is uh, current amplifying device, right? So out of these various structures, actually, that is this structure we consider as the modern days or present days, that is BJT, that is bipolar junction transistor, right? So that was also filed in 26 June 1948 and were awarded in. So now in this process, so here, then what was there? Now, based on this concept means here, that is this concept here, that is a grown junction transistor was fabricated, that is on June 23rd, that is 1948, right? So in this case, that is the first germanium, by using the germanium, first prototype that was made in 1949. So here the, I mean, point contact transistor was there, but first BJT based on germanium that was fabricated in 1949. Now Bell Labs announced Shockley's ground junction transistor on July 4, 1951. Now, in this process, that is Morgan Sparks, with the direction of Shockley, he developed the prototype of commercial BJT. So that structure actually it was simplified commercial BJT in 1951, and he also the same was licensed to a number of electronic industries, including Texas Instrument, to manufacture it. And he was the Morgan Sparks here, and this is Brett McEvoy. So she was the personal secretary of Shockley. So now here you can consider these things. That is, and in this development, just note carefully. So in this BJT development, there was no contribution of Barden and Breton. So Barden and Breton initially gave the concept of the point contact transistor, but modern BJT that conceptualized by Shockley, and it was implemented under his direction in 1949, and Bell Labs announcement made on July 4, 1951. And again at the same time also Morgan Sparks, they prepared the commercialized purposes the BJT structures, and license was distributed to various companies. Now, the little bit I will complete with this history of the transistor development, that is etymology of transistor. Then who gave the name of transistor? Where from this transistor name came into the picture? Now here, with this invention actually, that is no name was given by Bell Laboratory. Then AT&T Bell Laboratory was was in dilemma that what should be the appropriate name. So the lab authorities, asked for different names. So several names were given. Some, semiconductor tryout, because at that time, vacuum triodes, pentodes, all these things were existing. So semiconductor triode, surface states triode, crystal triode, solid triode, uh, iotatron. So these are the some of the names were coined for the transistor. But out of these things, R. Pierce, that he coined the name transistor. So, in his words, I would like to mention here, and at that time, it was supposed to be the dual of vacuum tube. So he just predicted that it could be a substitute of the vacuum tube, that is triode, and the vacuum tube had transconductance. So the transistor would have trans resistance, and the name should fit in with the names of other devices such as varistor and thermistor, just to maintain a name along with the varistor and thermistor. And since it is trans resistance, so he the trans register, so transfer register, so he gave the name, that is transistor. And there was a voting among all the employees, and they took the name suggested by J.R. Pierce, and the Bell Laboratory approved the name of this device as the transistor. So these are the small things which will try to I would like to inform you through this lecture. So J.R. Pierce actually they gave the name of the transistor of this modern device. Now, William Shockley, that is the another thing that you can consider, the Barden and Britain. Basically, they gave the demonstrate the point contact transistor in 1948, and then the PN junction semiconductors theory of PN junctions in semiconductors and PN junction transistors were published by William Shockley in 1949, and with the concept of the BJT. Now, this is the remarkable book, that is where the concepts of electrons, particularly concept of holes, and their various statistics which are used in the semiconductor device analysis, that was suggested by, published by Shockley in 1950. So here, the entire semiconductor theory was given by William Shockley, and the concept of hole, that was also introduced by Shockley. Okay, so you can say that theoretical study of semiconductor devices was, initiated with the theories suggested by that is Shockley. Now here that's a little bit about the field effect transistors. Uh, Now JFET, that was, as you have already mentioned, that is Lilienfeld and Oscar Hill, but that was never realized. But here JFET, based on the theoretical analysis, Shockley analyzed the working principle of the JFET in 1952. So these are the paper details. And the first working JFET was reported by Dassey and Ross in 1953, experimentally fabricated. And then MOSFET was first proposed and fabricated by Kang and Atala in 1960, both independently, that is, fabricated the structure. Then MESFET, another field effect transistor, almost similar to that of the Lilienfeld, was proposed by CA mid 1966, and the first working MESFET was fabricated by Hooper and Lehrer in 1967. That is, these are the some of the genesis of the field effect transistors. Now, JFET, if you consider, it was the basic concept was just like that one here. That is, one is source, another one is drain. It is something like that. This is connected to a tank. Okay, the water is coming here, and water is collected by this drain. But here, the gate is another controlling instrument, that is which can control the flow of this water that is from the source. Okay, the basic structure was just like that one. Here there is two p-n junction was used, so there was a n-type materials. So the p-type region was grown here, p-type region was grown here, so that one p-n junction will be formed here, another p-n junction is formed here. Okay, so either a single p-n junction can be used, or the both directions. Now in this case, the basic objective is there. Now if this p-n junction is reverse biased, and then there will be depletion region. So width of the depletion region, that will be increased by increasing the reverse bias voltage, right? So in that way, that is, if the both terminals are connected, okay, or the single junction is connected, so by using the reverse bias voltage, so this depletion region can be extended. So if this depletion region is extended, this one, then the channel opening, that can be controlled. So this channel opening, the basic objective was just like that. That is, here, that was just like a it was just like conductor. If you consider, then resistance R should be equal to rho into L by A. L is the length, so length is fixed. A is the area. Now, if this area is controlled, then resistance can be controlled of this channel. So, if the resistance can be controlled, then V by R, that is current, can be controlled. That was the basic motivation that is behind that one, right? So, this is the basic architecture of the JFET. Here, this PN junction, it is operated under the reverse bias conditions, and the current can be controlled by changing this voltage. Okay, so this voltage means here the depletion is, the electric fields are there. So these electric fields, actually they will control the current in this device. So that is why it is considered to be the, that is, field effect transistors. Now the consequently here, the this P junction, basically P plus N junction. Now P plus N junction is equivalent to that of a Schottky junction. So that is why the later case, that is, here this metal was used. The metal is such that its work function is higher than the work function of this material, so that it can form a Schottky junction. Here is the Schottky junction is formed. So due to the Schottky junction, now here, and if it is fabricated this one, then this structure we consider as the metal semiconductor field effect transistor, or MESFET, right? So MESFET, it has a, single gate structure that is being used here. So that is N plus region, N plus region. There is one is there is source, another one is drain, and this is the gate region, right? So this structure is considered to be the, that is MESFET, metal semiconductor field effect transistor. Now, next one that will coming to the invention of the MOSFET. Now, MOSFET, that is Mohammed Atala, he fabricated different structures. Out of these structures, he considered realized a structure like this. What he did here, it was an N-type semiconductor, P-type semiconductor, N-type semiconductor, right? And over these things, the entire region that he considered here, so that was an oxide region here, and in this case, that is this was a metal, that is actually gate, right? And this one N type, it was connected by a metal, and this was N type was connected by a metal. Clear? So NPN, this, so the one side is used as the source, another side was used as the drain, and that was used as the gate terminal, right? So then it was considered that that is the current between these two terminals that can be controlled by applying the voltage or potential applied to this third terminal. So that one is considered, we know that, so this is the first architecture demonstrated for the MOSFET by Atala, Mohammad Atala in 1960. Now, at the same time, that is contemporary, I mean, both independently, and there was no relation between these two. There is another patent was also filed, that is by Kang, I mean, Down Kang, in on May 31st, 1960, and he used the almost the similar structure is here. He used that it is a p-type region. Here is another p-type region, and he took this one as an n-type semiconductor, and p region was obtained here. Now this region was the one oxide region, SiO2, and by making a hole, that is a electrical contact was made to the p-type, p side, and there is another contact was made here, right? And it was the metal, that is gate was deposited here, that is the oxide. So that is again the current between these two terminals, this one, that was controlled by applying the voltage at this terminal, right? So that is another demonstration that was made for uh, the MOSFET by Kang. So Kang and Atala, they both gave the similar structure, similar structure for the, that is MOSFET in 1960, and both independently discovered the MOSFET, right? So these are some historical kinds of things. Now I'm just considering here. So basic structure from the Kang and Atala. Kang considered the NPN structure. Atala considered the NPN structures, and uh, Kang that realized this one PNP structures. So the basic structure is just like that one here. So it was a p-type substrate or an n-type substrate. It was n plus region or p plus region, and this was n plus region or p plus region. Here it is an oxide, silicon dioxide, and here it is an electrode, metal electrode. So this metal electrode basically, that is, we consider this one, that is these days actually we use a polysilicon, okay, for heavily doped polysilicon material. And this is another, that is electrode, this is another. So this is the basic architecture of the MOSFET structure. Now, if you look into this one, then you can analyze these things. So that is p-type substrate or maybe n-type substrate. If it is n-type, then it should be p plus region. If it is p-type, then it is n plus region, right? So one is source, another one is drain, and this is oxide region, and this is the gate region. So that is one voltage, gate source voltage, and that is drain source voltage, right? So this current flowing through this terminal, that can be controlled by controlling the voltage of that one. If you look into the lateral structure, it is just like an NPN transistor structure. If you got the vertical structure, then it is the metal, oxide, and semiconductor, and this is metal. So this metal is an ohmic contact here, ohmic contact, right? So now here we see that if we consider, if we replace the semiconductor by conductor, I mean, just imagine semi, if you just remove, then it is just like a conductor. So if the two conductor, electrode is also conductor, metal is also conductor. So these two conductors, and this is dielectric. So now you know that a parallel plate capacitor. So in between two, electrodes, if you place a dielectric, then it behaves as a capacitor. So this structure that behaves as a capacitor, which we call as the MOS capacitor. Why MOS means metal oxide semiconductor. Instead of conductor, it is semiconductor. So that is metal oxide semiconductor that will form as a capacitor. So the MOSFET basically can be considered to be the combination of a transistor and a capacitor. So the operation of the MOSFET that can be understood by the combined operation of the transistor action and the capacitive action. So if you look into this one, so this is if you consider here the transistor structures here, so then that is if you consider the energy band diagram, this NPN transistor, then you will get, so this is the common Fermi level. Fermi level is close to the conduction band in the n type, and it should be Fermi level close to the valence band for the case of p-type substrate, right? Now why I have drawn this energy band diagram. Now just see the electrons in the source side and electrons in the drain side, they are separated by this barrier. I mean by this energy barrier. Electron cannot come from this side to that side. So to come an electron from source to drain side, it has to overcome this barrier. That means electron has to gain sufficient energy to overcome, surmount this barrier and enter into the, that is, drain side, right? So that means no flow of electron that can take place as long as this energy barrier is there. Then what is to be done? Now in this case, now if we apply the potential here, positive potential here, so positive potential means energy is negative. That is minus q electron charge. If you multiply, then it will correspond to the energy. Negative energy means the barrier reduced. Now if we increase this highest, then this barrier height that will be reduced. So now this potential has to be supplied by the gate. Now just look into the structure here. So this is the point is here, right? So there is the NPN transistor. In this transistor, this is the middle region, that is base region. In this base region, actually, here, that means bias is applied here. So this applied gate bias, at this point, a potential is required. So this potential will reduce the energy barrier height between source and substrate and between, that is, substrate and drain, right? So here, so I mean here a positive potential is required to that of the gate region, right? So in this case here, then a positive potential is required here. So this positive potential, a certain portion of this potential, applied potential, will be dropped across this insulator, and a part of this potential will appear at this interface. So this potential will reduce the energy barrier between n-type and substrate, right? So this one here, now if we reduce further, then a point will be there when this level comes at parallel to this one. So then there is no energy barrier, so electron can easily, that is, flow from source to, that is, drain side by applying an electric field. So that is the basic mechanism to understand about the, that is, MOSFET. Now from the energy band diagram, if you consider, is the main MOS capacitor. So that is a heart of the operation of the MOSFET is the MOS capacitor. Now here I have just considered metal oxide semiconductor structure. I have considered ideal MOS capacitor. Now I have just assumed ideal means where I have just considered that, that is an ideal insulator, right? Ideal insulator. Ideal insulator means theoretically whose energy band gap is very very high, theoretically infinite. Now this is the metal and this is the semiconductor. An ideal MOS capacitor, so we have considered the Fermi level of metal and semiconductor, they are the same, right? So that is, if this is the vacuum level, now this is the phi m and this is the phi s, okay? Phi m, work function means the energy required to bring an electron from, that is, conduction band to the valence band. Bring an electron from the Fermi level to the vacuum, right? So that is phi m equal to phi s. That is in the ideal case. Now what happens? Now if we use a negative potential here to the metal side, to the gate side, then what will happen? Now since it is a capacitor metal side, if it is negative, the negative charge will be stored here. So other side should be must be positive charges. So the positive charges means where from the positive charges will come? That is all the holes. This should be accumulated near the interface, right? So all the holes should be accumulated in the interface. So that is called the accumulation mode of operation. So now if the holes, so concentration of holes will be more near the surface at this interface. So in this case, now the then what will happen about the Fermi level positions? Now just see that the Fermi level. Now once it is negative potential, means this energy should be go high, because that is Q into V minus Q into V, that is the energy. Now minus Q, V is negative, so both are positive. So whatever position was there here for this position, so this energy will go up. So at this, with this respect, that this energy has gone up by the QK amount, right? Once, so as a result of that one, if this portion goes high, then here, that is a tilt is there. So as a result of that one, an electric field will be flowing from the positive to negative side. So this is negative means other side is positive. So electric field is working in the direction. So this is the electric field, right? But here, these accumulated holes, they cannot come to this side because here it is an oxide region. Okay, so there is no possibility that the holes can come across from this side to that side. Now, as a result of that, what will happen? Now, because of the storage of the accumulation of the holes here, so the Fermi level, I mean, valence band will be moved closer towards the Fermi level position. So band bending will be taking place this one. Now, if the potential is greater than zero, then opposite phenomenon will take place like this. So band bending is taking place here. Now, the interesting portion is that if we apply the positive potential is here, so this energy level will go down. So energy level it is going down. Fermi level is that is fixed at the fixed position here of the semiconductor side. So then what will happen? So band bending is taking place in this side. So we know that intrinsic Fermi level that is close in the middle of the band gap. So now this Fermi level position is fixed of the semiconductor. Okay, so now here the intrinsic Fermi if we apply more positive voltage, then a point will come when this point will meet at this point. That is intrinsic Fermi level and Fermi level position, they will merge together. Then when does it happen? When the intrinsic Fermi level are the same. So that is only when, that is if the semiconductor is an intrinsic semiconductor. So if we apply a potential here, a point at which this point will coincide here, then the interface will behave just like, as an intrinsic semiconductor, right? Now if we increase further, then what will happen? Then further band bending will take place, and because of this band bending, now here what will happen? That is, this intrinsic Fermi level is coming below of this Fermi level. That means the Fermi level is lying above the intrinsic Fermi level near the interface. When does it happen? When the Fermi level is above the intrinsic Fermi level, that is only in the case of N-type semiconductor. So then, in other words, we can say that is interface at this point, the interface will behave just like an N-type semiconductor. So this particular phenomena we considered, we call it as the surface inversion phenomena, right? Surface inversion phenomena. What is this? Now, if we apply a gate voltage beyond a certain case, so then the that is the interface of the substrate near the substrate that converts into from P to N type. Okay, so as a result of that one, here, once it converts into N type, there are a lot of free electrons will be there. So this is the free electrons uh, available in the inversion region, right? So this is basically, and that happens only in a very small region. You can consider that is within this region where the crossing is taking place. Within this region, a very thin layer of electrons will be there. Now, initially, when this voltage is positive, then what will happen? Because of this positive charge, their negative should be there. And electrically in this side, that means because of this positive, all the holes will be departed from there. So that reason that initially the depletion region will be created. Now, after that, when the potential is much larger, then from this to this region where the band bending is taking place there. So this region from this crossing to band bending, it should be a depletion region, and from crossing to this one, very within few nanometers, very thin, there should be a thin layer of electrons here. That is due to the surface inversion. That is the substrate has been converted from P type to N type, right? So as a result of that, what happens? So if we come to here, so then we can say that that is once we make this potential sufficiently large, then an electron layer will be formed from source to drain. So as a result of these things, these electrons completely will be there. So we call it the formation of channel, right? So if you, I mean, consider about the surface potential phi s, if you plot theoretically, I've taken it from statement, you can follow any textbook. So if this, as long as gate voltage is negative, that is surface potential is negative, then this is the whole concentration here you can consider that is exponentially increased with the negative surface potential. Now with the positive potential, then initially up to certain region, that is it should be, that is depletion region, then the weak inversion region will be created. What is weak inversion? Now, once it enters below this one, and then the N channel region is formed. But this electron concentration may not be as sufficiently large to contribute a significant current, right? Now, if you can create a condition that is where that is this difference, this is called the Fermi potential. Now, if the separation between the intrinsic Fermi level and this Fermi level, and if you make the penetration, I mean this intrinsic Fermi one, when these two will be the same, then we consider the strong inversion. That is the electron concentration should be as good as that of the whole concentration in p-type substrate, right? So here, so this is the weak inversion. In this region, the electron concentration, that is inversion takes place, but the concentration of electrons are very small. Okay, so that is called the weak inversion region. Now after that, if we increase this surface potential further, then electron concentration will be exponentially increased, and that we consider as a strong inversion region. So current, significant current will be flowing through the device. So here we have to operate, that is in this. Now, when we consider the strong inversion starts, then depletion region, that is the maximum depletion region, and no further depletion region will be created there. So there is a maximum depletion region happens that. Now, here some important phenomena, I mean terminology, that is total flat band voltage. Flat band voltage, that is here we just consider, we just define, you can follow any textbook there. So flat band voltage, that is actually phi ms, that is the work function difference between metal and semiconductor. Now in this ideal case, we have considered the work function of the metal and work function of semiconductor is same, but for a practical one, they are not same. Secondly, the oxide that we have considered is an ideal oxide, but practically it is not ideal oxide. And in an ideal oxide, there are no charges. But in the practical oxide, SiO2 and some many practical oxides, there are certain fixed charges are there. So because of these differences, work function are not different, are not same for practical metal semiconductors and metal MOS capacitor, and again oxide is not an ideal one. So for any practical MOS, so due to this difference in work function, and there are oxide charges, that is insulator QI, we have denoted the charges in the insulator, and here the oxide capacitance CI. So this oxide capacitance means that we have considered, that is if you consider here, that is oxide capacitance per unit area, that we can that is considered here. So that is permittivity, right? Permittivity of that one divided by its thickness. Okay, so this is the oxide capacitance per unit area. Now, here in this case, so due to these things, that is one voltage is required, this amount voltage is required to make it a practical MOS capacitor into an ideal MOS capacitor. So this flat band voltage, you can realize this is the gate voltage that is required to make an practical MOS capacitor into an ideal MOS capacitor. And threshold voltage, this is defined by these relations here, Vt, threshold voltage. So phi ms, this is the difference in work function between metal and semiconductor, and this is the oxide, whether the insulator charges, that is insulator capacitance, right? Here phi f is the that is Fermi potential. Fermi potential, that is actually kT by q ln, that is Na by Ni, that is Fermi potential, right? So this is the some relations are there. This is the on-state current and this is the off-state current. That is off-state current particularly that happens. That is here you see that. So this weak inversion, strong inversion means we consider the device is on, the MOSFET is on, channel is formed. But in this weak inversion, officially we are treating this one, theoretically we are treating it as an off-state. But in the off-state also, since the inversion layer is created, channel is formed, due to that one also, some current should be observed. So theoretically, we do not, we never want that there should be any current, but still we get a current, and that is called the, that means sub-threshold current. Sub-threshold means below threshold current. Okay, and the gate voltage at which the strong inversion starts, beyond which the strong inverse starts, that is called the threshold voltage, right? I mean the device is turned on, that is called the threshold voltage. So this is the on-state current is here, and this is the off-state current is here. Now here are some important things that I would like to mention here. Now this work function difference, okay, and this is nothing but that is VMP, right? That is flat band voltage. So threshold voltage that can be controlled by the flat band voltage, and flat band voltage that can be controlled by the work function difference between metal and semiconductor, right? And again, this portion, that is oxide charges, insulator charges, that can be also, that is minimized. Okay, but that is mostly beyond our control. But somehow by improving the fabrication techniques, the QI can be also optimized. Now, so this phi ms is one of the important parameter in controlling the threshold voltage. What is phi ms? The difference of the work function, the work function of the metal minus work function of the semiconductor. Now, another important parameter is the doping concentration. Now, if the doping concentration that is increased, then threshold voltage will be increased, right? Now, the another important parameter is CI. CI is the oxide, I mean insulator capacitance, the oxide capacitance. Oxide capacitance means oxide permittivity divided by oxide thickness. So, the oxide thickness, if it is reduced, then the capacitance, oxide capacitance or insulator capacitance can be increased. Now, once the oxide capacitance is increased, then what will happen? Threshold voltage will be decreased. Right? So, just visualize these things. If the oxide thickness is reduced, then capacitor will be increased. Oxide capacitance will be increased. That is, threshold voltage will be decreased. Right? So the main parameters, if you look into that one, threshold voltage, then phi ms, doping concentration of substrate, and the thickness of the oxide. Right? So thickness reduction in oxide thickness will reduce the threshold voltage. So increase in doping concentration will increase the threshold voltage, and increasing the difference between work function phi m and phi s, then also we can control the threshold voltage. On state current, if you look into this one, it is proportional to mobility. Okay, carrier mobility. mu1 is the mobility, z is the width, and ci is the capacitance, and l is the, that is length, channel length. Right? So channel length means that you can consider that is this, from this region. So from this to this region, that we can consider the channel length, right? So now what we are getting ultimately, so that see, this current is proportional to mobility, proportional to oxide thickness, but inversely proportional to L. So if the channel length is decreased, then current will be increased. Now, if oxide thickness is decreased, then current will be increased, because oxide thickness decrease means Ci is increased, so it can be there. And if the mobility is decreased, then the current will be degraded. Subthreshold leakage current, which is completely undesirable. Okay, we want that this current should be zero, but here if you get this relations here, you can neglect this term, but it is Vg minus Vt. Now just see, if any case, for a fixed gate voltage, if the threshold voltage is decreased, then that is, this unwanted current will be increased. That means if there is a degradation or reduction in threshold voltage, then that is subthreshold leakage current or subthreshold offstate current, that will be increased. Now, why this current is so much important? Because offstate current theoretically should be equal to zero. Okay, but if we reduce the channel length, then this oxide current, this offstate current will be also increased, right? Now, if this current is increased, that means just imagine the device is off, but still a current is flowing. So this current will create a loss, which is I square R loss, which is complete, and we have power dissipation, which is completely, that is undesirable, right? So that means we have to minimize this current as small as possible. Ion or on current should be large, so that ion by IOF ratio should be very large. If the ion current is large, then that means we can get in the IC logic circuits, we can get the fan out will be more. Okay, so and device can be easily used to drive the other circuits. So these are some of the important parameters that we have to look into. Now here, how the phi ms can be controlled? Now phi ms, if we have a fixed metal and fixed semiconductor, okay, so silicon, so for the silicon actually, that is work function can be controlled by the doping, right? Now if we fix the doping, then its work function is fixed. Now if we fix metal, then work function is fixed, so we cannot have any variation. So that is why the metal electrode, the gate metal, that is being replaced by polysilicon. What is the beauty of polysilicon? The polysilicon, if we just use, now here a little bit I would like to mention, for any semiconductor, if the doping concentration is increased, and doping concentration is increased beyond a certain level, which we call the mode transition level, then every semiconductor starts to behave just like a metal. And here this property is used. The polysilicon is heavily doped, and as the doping is increased, then it behaves just like a metal. So the polysilicon, again, it is compatible to the SiO2. Okay, so the device fabrication will be much easier. So now in this case, I have shown that by using the doping of the polysilicon here, that is the work function difference, the phi ms metals, work function of the metal semiconductor one, that can be made as a function of the doping concentration, right? So that is for p-type and n-type, and p-type polysilicon, n-type silicon, p-type polysilicon, p-type silicon. So in this case, it is decreasing with the doping concentration. It can be increased the doping concentration. So that is to say that we have the tool to control the phi ms if you replace the metal by polysilicon. So that is why mostly the polysilicon is used to get a uh, better controllability on the phi ms and then on the threshold voltage. Now, next invention I am just coming to here, that is the invention of integrated circuit. Now, the first integrated circuit, it was reported in 1959. So basically, it was demonstrated by Jack Kilby on September 12, 1958 at the Texas Instrument. Here is a little story is there. At that time, Jack Kilby just joined the Texas Instrument, and as a newly appointed scientist, as per the rules of the Texas Instrument, they cannot enjoy the summer vacation. So in the summer vacation, that is, Jack Kilby was alone. He could not get the opportunity to enjoy the summer vacation. So then he assigned a project for himself. He just took the project that is to design the electronic circuits and to incorporate more and more number of electronic components in a circuit. Okay, but that is he gave this name of this project as the tyranny of numbers. So how many numbers can be that is practically incorporated in a circuit, physical circuit? But he was completely tired that he wants the number of transistors was more than 3 or 4. That was very difficult to make a circuit in a, because at that time also that means it was very difficult. Then he came up with a concept, that is how with the minimum effort, that is the components can be integrated. Okay, and his concept he demonstrated on September 12, 1958 at the Texas Instrument, and then he filed a patent on 6th February 1959. And in this patent, he just claimed that a body of semiconductor material wherein all the components of the electronic circuit are completely integrated. Now, for this IC, he used, that is, germanium. He did not use the silicon, but he used the germanium. And here it is one sort of considered the hybrid IC structure. Here, there is some of the components, I mean circuits, they were, that is, wires were connected externally also. Okay, so some internal connection as well as external connections was there. So that was the first integrated circuit that was reported by Jack Kilby on September 12, 1958. Now, at the just few months later, that is another concept, that is the very interesting concept that was reported by Robert Noyce, and he gave the concept of the monolithic integrated circuit. And here, as we mentioned, the difference was that in this case, some external connections were there and some internal connections were there. Okay, but it was more compact. That is on the same chip. That is all the interconnections could be made, and he demonstrated just 4 months later, 3 4 months later. That is, it was demonstrated by Robert Noyce, and he used the silicon, but Kilby used the, that is, germanium. And in this case, the Robert Noyce, he used the Jean Hornis planar process and Mohammad Attal's surface passivation process, and that was, he reported the first integrated circuit uh, in Fairchild Semiconductor. So now, here just little bit of a summarize. So Jack Kilby, he was Nobel laureate in 2000 and co-inventor of the IC's 1959, and he was the founder of the Texas Instrument, and he also invented the pocketronic calculator actually in 1967 by using his own method of integrated circuit technology. At the same time, Robert Noyce, that is, he is also claimed to be the co-inventor of the integrated circuit in 1959, and he founded the Intel in 1968. And he also co-founder of the Fairchild Semiconductor Corporation Limited. And at Intel, Robert Noyce managed and he first invented the revolutionary the microprocessor system. So Intel, that the first microprocessor that was conceptualized under the by using the concept of the Robert Noyce. Now there is a conflict. Then who is the inventor of the integrated circuit? Huh? So either Kilby or Robert Noyce. Now Robert Noyce moved to the court, and there was a long, legal battle was going on, and court was totally confused that who will be given the credit to the invention of the integrated circuit. But once the court case was there, but in the meantime, the integrated circuit technology was developed by leaps and bounds, and that is who is the inventor, it does not matter, but mostly the concept of Robert Noyce, that is that was explored. Intel, once the microprocessor was introduced, then growth in microprocessors and any other complex IC technology that is developed based on monolithic integration techniques of Robert Noyce, whereas Jack Kilby's, that is IC concept, was somehow, that is hybrid kinds of things, but monolithic concept by Robert Noyce was mostly explored. So then, unfortunately, in 1990, Robert Noyce he expired. So now, he expired in this one. So now, on the basis of that one, in 2000, Jack Kilby was awarded the Nobel Prize for the invention of the integrated circuit. Now here, that is in Intel, that is Robert Noyce was already in Intel, and Gordon Moore also, he that is both founded the Intel in 1968, and both left the Fairchild. Oh, hello, hello. So Gordon Moore and Intel, they established the Intel in 1968, and both left the this one. And at that time, the revolution of planar IC technology that started, miniaturization of transistor, that is that started to integrate more and more number of transistors in the, because after invention of the microprocessors, then it was started how to improve the functionality of microprocessors, and how to develop that is more powerful microprocessors. So at that time, more and more number of transistors were required to be integrated there. Now, when the Nobel Prize was awarded to Jack Kilby, so then what happened? So due to this, complexity of microprocessors, so then by using these things, the various digital systems where complicated circuits were implemented, and the mm, functionalities of this integrated circuit, that was more so the same IC, for example, op-amp, the operational amplifier you can use as an adder, as an subtractor, as an wave shaping circuits, inverting amplifier, non-inverting amplifier, many more. All kinds of computational works can be done by the same integrated circuit IC. So that is complicated functions are operated. So at that, as a result of these things, that is functionality, that is of the circuits, that was there, and the cost factor was reduced drastically. That means if you if you implement this circuit by discrete components, the cost will be very, very high. So in his Nobel lecture, Jack Kilby mentioned that what we did not realize then was that the integrated circuit will reduce the cost of electronic functions by a factor of 1,000,000 to 1. Nothing had ever done that for anything before. So the whatever the cost was there, the cost factor that was reduced from 1,000,000 to 1 by with development of the integrated circuits, right? So now next started, that is to increase more and more number of transistors. Then it was started the scaling process. What is scaling? So the MOSFET scaling basically miniaturization process. So I pictorially I have just shown these things. So that is one device. I want to get a replica of that one. It is a smaller version of that one. But my demand was that is at the time the demand was that we are reducing the size only. But whatever the characteristic feature of the device was there, the same characteristic feature should be there. Okay. So what is the use of that one? The miniaturization of the MOSFET, that basic objective was that to lead to the packaging of more and more number of devices in a given chip area. Okay. Why? With the similar functionalities of a chip in a smaller area. So the basic objective is that whatever one IC is there, I want to fabricate this entire integrated circuit in a smaller chip area. Okay. And so that at the same chip we can develop, that is that complex circuits with, that is much higher functionalities in the same area. That was the basic motivations of the scaling or miniaturization of the MOSFET technology. Now there are, that is several techniques, scaling approaches were there. So there is scaling theories. There are three scaling theories were there mainly: constant field scaling, constant voltage scaling, and generalized scaling. These are the three scaling techniques are there. Now in the case of constant field scaling, that was suggested by Denner et al. In a IEDM conference in 1972. Later it was published in the IEEE paper. In the constant field scaling, what was done? Now the basic objective everywhere in the device, what was the electric field there in the larger version of the device, the same electric field should be maintained in the smaller version of the device. So that is basic objective is the electric field, we know that voltage divided by length. Okay. So the if the voltage is reduced by a factor, that is V is replaced by V by S and L is replaced by L by S, S is the common factor, then the electric field will be the same. So that was the constant field scaling. So this suggested that all the voltages should be scaled or should be divided by a factor S. All the dimensions, this should be also divided by a factor S. And since the oxide thickness that is reduced, so gate oxide capacitance will be increased. So that will reduce the threshold voltage. To compensate the threshold voltage, the doping concentration has to be increased. So doping concentration was increased by factor of S. That was the, that is reason for that one. So here the objective of all the voltages, all the dimensions were divided by S, but except the doping concentration of the substrate, it was multiplied by S. So that everywhere electric field should be done same, and whatever degradation took place in the threshold voltage, that will be compensated by the, that is increasing the doping concentration. Right now, what should be the value of S there? Now S was selected to be 1.43 and 1 by S, that is 0.7. That is the size reduction whenever we are moving from one technology node to another technology node, then the size reduction should be, that is 30%. Okay. That means suppose if we consider there is a 90 nanometer technology is there, once we move to the next technology node, then 90 into 0.7, that is equal to 63 nanometer. So we have come to this near about 65 nanometer technology, right? So all these technology node that we talk about, 90 nanometer technology. So next generation should be, we have considered 65 nanometer technology. Then again, if you 65, if you multiply by 0.7, then we have come to around, that is 45 nanometer technology. So that is why whenever a technology generation node will move from one to another, that is almost nearly reduction should be about, that is 30%, right? Then what is the effect? Now device by die area. Now just consider initial area was W into L. Now it should W by S, L by S. So the reduction is 1 by L square. That means nearly 50%. That is chip area reduction is there. So now transistor density, what will happen? So that is whatever area of transistor was there. So now at the same area, we can fabricate that is two transistors. So number transistor density that was increased by twice. That means that is density of transistors in the IC by using this scaling theory can be double. Now another important parameter that we consider here, that is gate capacitance. So it is reduced, drain current now, because L is reduced, right? So now in this case it is, that is 0.7. So drain current reduction is taking place. Gate delay, that is C into V by I, that is RC. So that was around 0.7. Power dissipation, now that is another important factor. Power dissipation was reduced by 50%. Okay, but power density it was remaining same. So the power dissipation that is used, that is reduced by 50% in the case of, that is constant field scaling, and frequency of operation that is 1.43, I mean, times, right? So frequency, when I mean by using these things, the frequency of operation, the speed of operation was increased by 1.43 times. Power dissipation reduction was there. So it was considered to be, that is low power application, it is fine because power dissipation is less, 50% power dissipation is reduced, chip area, I mean density is increased, but frequency, that is speed, is improved, but not so rapidly. It is around 1.43 times. So this technique is suitable for the low power applications, low power VLSI applications. Now the another techniques that was scaling theory was there, constant voltage scaling. The constant voltage scaling here, it was mentioned that, that is voltage everywhere, maintain the voltage is the same, whatever voltage is there, you keep it the same voltage, only the dimensions reduction should be L by S is again 1.43 times. Okay, but doping concentration again N by Na into S times. So constant field scaling, both were scaled. Now here voltage are not scaled, only the dimensions are scaled. Okay, all the dimensions, and doping is multiplied by S times, right? So this is the constant voltage scaling. Now here the problem was that since V was fixed, no change, but dimension length was reduced, so the electric field was very high. So if the electric field was very high, then the problem was that, that is the, there are several other effects was there because of the high electric field, right? So to minimize these things here, what is done? So another constant volt scaling was there. So in the modern constant volt scaling, it was considered that no, we can also reduce these things. The voltage are scaled not by S, by a different factor beta. Beta should be greater than 1 but less than S. S is equal to 1.43, but it was around 1.1, 1.2 or something like that. I mean smaller reduction in the voltages should be there. So that electric field, there is can be make a trade-off between the increase, the electric field should not be increased tremendously. So it was there. Now another one, it was considered the quasi voltage scaling. So in this quasi voltage scaling, it was considered that because S was a different factor beta. Okay, so beta again, it is smaller than the S. So the gate oxide reduction, oxide thickness was as more small, so it should not be reduced drastically. Okay, so that is another, that is quasi constant voltage scaling. Here we use a different factor. I mean S is applicable for other dimensions but not for oxide. For oxide we can use the beta scaling. So that is, we can consider the quasi constant voltage scaling. So these are actually, I mean some kinds of modernization here are there, but actual constant voltage scalings are there. All the voltages are constant and only the dimensions are scaled down by S factor and doping concentration by S factor, right? Now here the interesting portion is that the reduction of size is 50%, transistor density again double, so the drain current that is increased, Earlier it was decreased, but now it is increased. And speed, the important thing is that speed has become double, I mean twice, more than twice, that is double. And power dissipation has been increased. So earlier power dissipation was 50%, now it is 1.43 times, but speed has been increased. So here the constant voltage scaling, the in one way we are getting that speed is very high. On the other disadvantage, you are getting the power dissipation is more. So these devices here is this scaling technique was used for the case of high speed ICs. So all the high speed computational purposes, the microprocessor processors which are developed for the high performance computing cases, so there this scaling is suitable where the power dissipation is but at the cost of increased power dissipation, right? So speed, high speed we are getting, but at the cost of high, that is power dissipation, right? So the both things are contrary to each other. Simultaneously, we cannot do that increase in speed and reduction in power dissipation. That is not possible. And however, we can make a trade-off of that. So active power dissipation per area, that was 2.92, almost three times. That is a very that is serious issue. So this technique is not suitable for the low power applications. So in that way the VLS, I mean IC technology also, that was grown into two ways. One is low power applications and high speed applications, right? So time is short, I have just summarized these things here. So these are the just compared, that is different scaling rules, summarized these things. Now here, why this? Now in this way, initially when these techniques were there, there is one of the common in 1965. 1965 is 1965. That is, it was Morse predicted that the number of transistors in an IC that will be increased, I mean, will be twice every year. Okay, and that was followed in between 65 to 75. Now in 1975, then he modified these things, that because once we started from 10 micrometer and up to 1975, then certainly the further we reduce, initially there was no effect, but once the size was reduced, geometrical size was reduced, several other effects that is dominated. Okay, so then the that Moore that changed his prediction, and in 1975, and he just predicted that that is the number of transistors that can be placed inexpensively on an integrated circuit will be doubled approximately every 2 years. Some people say that 1.5 years, but Morse predicted that every 2 years, that is number of things transistors will be become double. So it was, I mean, he predicted that, I mean, it is still valid now, and it is predicted that this can go up to 2029. So this Moore's law. So I'm just quickly trying to summarize here. So we just try to these things. If you consider the number of transistors, it was, I mean, only that is very few. I mean, less than 10, around 10 in 1970, and which in 2010 is 2.3 billion transistors, and now it is more than 4 billion transistors at the present situation. And the channel length, if we considered, we started around 10 micrometer, and now we have reached to around, that is 7.4 nano. I mean, we are talking about 7 nanometer technology. So that means drastic change that has been taken place. And transistors per processor chip, we just see we have reached around 4 billion to 4.5 billion transistors, that is at present. Now, if you consider gate length, it has been decreased by 100 times. Junction depth, it has been decreased by 100 times. Gate dielectric thickness has been decreased by 100 times. Supply voltage has been reduced by 10 times. Chip area has been increased by 10 times, because more and more number of, I mean, complexity of the circuit uh, in complex microprocessors have been there. Clock frequency, it has been increased. The frequency has been increased almost 1000 times. And power consumption, that is also increased by these things. Okay, so increasing frequency and simultaneous power consumption, that is also increased. Now here, long channel versus short channel device. Point we consider a long channel device and a short channel device. The long channel device that we considered, that is when the channel length, and this is the depletion region. So if XDS and XDD, they are comparable to the channel length, uh, then we consider the short channel. Now if L is greater than XDS, where XDS, this is the depletion region, N plus P region, N plus P junction. So once the depletion region XDS is negligible as compared to channel length, and XDS is liable to this one, then we consider the long channel, otherwise it should be the short channel device. So in the short channel device, what will be there? When L is less than equal to this short channel device, several detrimental effects will be there. Here what happens? The threshold voltage reduction due to charge sharing phenomena takes place. So in this case, what's happened? Actually, the device is off. Device should be off, but it is showing a large current is flowing through this one. That is due to the very small threshold voltage. Okay, as we have considered, reduction in threshold voltage will be increasing the sub-threshold leakage current. Then DIBIL, drain induced barrier lowering. Now, threshold voltage, as we have shown that it is independent of the drain voltage, but in this case, threshold voltage becomes a function of the drain voltage. If the threshold voltage, drain voltage increased, threshold voltage will be decreased. Now, pass-through phenomenon will take place. Pass-through phenomenon is when this depletion and this depletion is merged together, then electron can be directly tunneled from this to this, can be drifted from source to drain without depending on the gate voltage. So that is called the pass-through phenomena. Surface scattering phenomena, that means under this condition due to large electric field, gate oxide electric field, the carrier, they will be scattered, so that the mobility will be degraded due to the surface scattering. Now velocity saturation, because due to high electric field, we cannot get a linear region. Mostly the device is either on and off. These two positions are there. So linear integrated circuits are not possible. Impact ionization, because of the high electric field, so the avalanche multiplication will take place. As a result of that, that is this drain channel junction that can be broken. So breakdown takes place. So large drain current can be there. Hot electron effect, the due to electrons are having very high energy. So due to high electric field, so because of this high electric field, because you know that velocity equal to V equal to mu into E. So if the electric field is high, then velocity will be high. Then half m v square kinetic energy will be high. So as a result of that, electrons, a large of the number of the, and this, if this thickness is very small, then electrons may penetrate from this to this one. The gate leakage current will be increased. Okay. So these are some of the effects. There is a long channel and this is short channel, and then the DVI effect will take place. This is the pass through. When these two are merged, electrons can be directly tunneled from this to this side. And here velocity saturation, that is there. So this linear region will be very small there. Sorry. So I am just going through this one. Avoiding this time is short. So now effectively what we are considering here, now long channel, now what will happen due to the scaling? Now due to the scaling, what is happening? So the transistor size is reduced. Now here two effects, decrease in oxide thickness and channel length. As we have mentioned, oxide thickness, if the oxide thickness is reduced, then gate capacity, oxide capacitance will be increased. If the gate oxide capacitance is increased, then what will happen? Threshold voltage will be reduced. If the threshold voltage is reduced, then gate leakage current will be increased, right? And simultaneously, the surface scattering will be increased and mobility of the carriers will be decreased. Now, decrease in channel length, what will happen? Electric field becomes two-dimensional. Threshold voltage will be dependent on the drain voltage, that is DIBL phenomena will be increased, and then all the subthreshold leakage current, that also due to quantum mechanical tunneling will be increased, and that also increase the hot electron effect, right? So these are some of the detrimental effects. So they arise from the scalings. Once we are reducing the size, minimizing the size, then simultaneously that is these detrimental effects will be there. Now the techniques to be there to minimize or to optimize these adverse effects. So that is why the non-classical MOSFETs that were introduced to avoid all this, because we have to minimize the device, and if you want to minimize this device, then gate leakage current will be increased, okay, because of the direction of the oxide thickness, and carrier mobility degradation will be there, substitute leakage current will be there, I mean offstate current. On the other way, channel length reduction, once it takes place, then the hot electron effect is increased, so all the DIVL is increased, so all this phenomena that has to be nullified. So for that one, non-classical MOSFETs, that means the normal MOSFET structure that we have considered, so that has to be, are no longer valid. They have to be changed or modified. So there are several techniques are used. Substrate engineering technique. So in this case, that instead of a simply P silicon substrate will not work. We have to change some new substrate, just like SOI, silicon on insulator substrate, or some other substrates. Structural engineering. So we require new device structures. Gate structure engineering. Now here, gate structure engineering, several things we can consider. Instead of single gate, we can use the multi-gate structures, maybe dual gate, triple gate, gate all around. All these structures can be there. Gate electrode work function, there, gate electrode work function, whatever the gate metal we are using, we can use some, instead of a single gate electrode, we can use the multiple gate electrode structures. And gate oxide material, instead of SiO2, we can use other gate oxide material, just like Al2O3, aluminum oxide, and hafnium oxide, and the gate structures also can be used. Channel profile engineering, we can use undoped channel or channel with various non-uniform doping profile in the channel. Carrier mobility engineering, that is carrier reduction, that by introducing the strain in the channel, we can use the carrier mobility of the channel. And channel material engineering, that we can use, instead of silicon, we can use, that is many other materials, like, so maybe gallium arsenide, 3,5 compounds, and many other materials, germanium, and many other structures we can use. So these are the different modifications can be made to have some new features of the transistor, MOSFET transistors to eliminate it. Now we'll consider some of the structures. Now here it is the SOI MOSFET. So here silicon on their buried oxide. Now in this oxide here, right? So this is the channel, silicon channel, right? So after that, this is oxide and graphite. So this is the, hello, हाँ हाँ ठीक है बंद कर रहे हैं just. So these are the SOI technology. So now here, so instead of single gate, we can use the double gate structures. So in a single channel, we can get a double channel. So we can get the, that is current, twice of the current. So current degradation that can be avoided. So these are the DG MOSFET structures. So here the different gate structures. Here in that way we can consider here top gate, bottom gate can be this one. So they have their own problems. The alignment of the gate structures are the difficult problems are there, but that can be there. Here, instead of a single metal, we can use the gate of double metal structures. So that is called the dual material double gate MOSFET structures. Now, instead of dual gate, that's triple gate MOSFET structures. Here, three metals are used. Only thing you have to maintain that the work function of the metal 1, 2, and 3 should be such that phi 1 should be greater than phi 2, should be greater than phi 3. So in that way, that is we can use the structures. Now, again the FinFET structures. Here we can consider here the silicon, this one. So we can consider the gate like that. It is the thick dielectric. So here the channel will be formed in this side and in that side. And here gate all around structures. So in all sides it is there. So there is one channel, two channel, three channel, four channels. So four channels can be formed so that the control over the of the gate on the channel can be increased. So that can be another structure. So it is the gate all around, the cylindrical gate structure device. Here In this case, silicon channel is strain is used silicon germanium on that silicon channel is gone, so that that is strain engineering can be introduced to is performance. Junctionless transistor. Now in this case, we can use a single transistor. Here it is there is no junction. Both are the same semiconductors. Here n-type semiconductors are there. Okay. So now, I mean, by controlling the gate voltage, so it is fully depleted this one. So now once we increase the gate voltage, so a channel is formed. So the conductivity of the channel can be modulated to get this structure. So that is another junctionless structure. Here instead of continue, I mean a Gaussian doping profile can be used to change these things. Here another junctionless structure where a pocket can be introduced, that is to control the characteristics of this device. And now another important structure which is the hot topic is this, that is the tunnel field effect transistors. So it is basically a PIN diode with a gated junction. I mean gated PIN diode. So the main advantage of this, so this is another structure. The working principle we can consider here, it is something like that. Here this conventional MOSFET is this one, but here tunnel is this one. Here the total mechanism is maintained in such a way that under a gate bias is applied. So then the electron from the valence band of the source is tunneled through the to the channel that is at this junction, okay. So that is tunneling mechanism that is being explored here. So this is another structure where that is doping less. So here you just use this hafnium, and this is platinum here. So N plus regions are not doped, and because of this metal, the virtual plasma doping is used to get the better performance of the device. So here the stacked gate oxide high K and SiO2, instead of using a single metal oxide, we can get a stacked structure, vertically stacked structure, high K HFO2 and SiO2 structures, and rest of the things as a tunnel out. Now here this tunneling mechanism is taking place. So this is a vertical T-FET structure. So here that is entire T-FET is can be grown vertically, and a high that is doped resin, that is pocket resin, can be introduced, and that can be used to control the characteristics of the, that is vertical T-FET. So now the conclusion that we have several short channel effects in nanoscale MOS transistors have restricted the scaling of CMOS technology. So these detrimental effects can be optimized through structural engineering, material engineering, high K gate oxide engineering, substrate engineering, multi-gate engineering, channel strain engineering, and gate electrode engineering of the MOS transistors. So now now I will conclude with this one. On 13 April 2005, Gordon Moore was asked that is how long your theory, I mean your uh, law, that Moore's law, can be valid. So he just mentioned that it can't continue forever. The nature of exponential is that you push them out and eventually disaster happens. And he predicted that once the diamond transistor size reaches at the atomic levels, then actually that is it has to be, I mean, some alternate method has to, I mean, his law may not be valid. So thank you for your kind patience. I took some more time, I think so. So okay, I can conclude. I can conclude here.
Okay, dear participants, if you have any query, please unmute your mic and feel free to ask. Okay, sir, I have a query related with this session. Is there any deciding factor by which we can find how much we can miniaturize the size of any IC or chips?
I mentioned that AC is considered, AC is selected to be 0.7. Whenever one technology node to another technology is move, we select that. That is 0.7 is the factor decided by the, I mean, internationally it has been decided. So that just consider 90 nanometer, the next nanometer technology will be equal to 90 into 0.7. that is equal to 63. So 63, that means we have just we have considered as a 65 nanometer. So again 65 nanometer, next technology will be given, just multiply 0.7. So it should be around, I mean, 45 nanometer technology. Again 45 into 0.7 will come to around 32 nanometer technology. I mean, in that way actually, uh, around, I mean, approximately 0.7, not exactly 0.7, but factor is decided as 0.7. This is the technology note.
Okay, sir. Thank you, sir. Is there any query? No. Okay. A very good afternoon to everyone present here. On behalf of Electronics Engineering Department of IERT Prayagraj, I Jitan Kumar Shukla deem it a great honor and privilege to summarize this session and to propose a vote of thanks for this motivational and informative session. I use the term motivational for this session because the way Professor Jit sir started and progresses in his talk is truly motivational and inspiring for us as a faculty member to generate the interest in our talk or topics. So first and foremost, we Electronics Engineering Department of IERT Prayagraj would like to express our heartfelt thank to Professor Jeet sir for sparing his valuable time for this session. During this session, Professor Jeet sir explained the various topics starting from their history to the advanced concept of the topic. In this session, he explained the early research in semiconductor devices and their various basic concept of the diodes, bipolar junction transistors, field effect transistors. He also explained he also highlighted the contribution of various eminent personalities in the field of semiconductor devices such as J.C. Bose, William Shockley, Gordon Moore, Robert Royce, etc. In addition to the field effect transistor, he also highlighted the modes of operation for the MOSFET capacitors and its importance in the device modeling. Mm, He explained the different parameters, important parameters for MOSFET, such as flat band voltage, threshold voltage, on-state current, and their effect on the device performance. He explained the various interesting information about the integrated circuits and miniaturization of ICs by explaining the various scaling techniques through which we can minimize the size of an IC or chips and their limitations also, and how these scaling factors affect the device performance, such as short channel effect. He also highlighted the various structures that helps to overcome the shortcomings or problem arises for during the size reductions. And these concepts are silicon insulators, FinFET structures, strained Si MOSFETs, junctionless transistors, etc. We as an organizing team do not have sufficient word to express our gratefulness to Professor Satyabrata Jit sir for accepting our invitation and for enlightening us. Thank you very much, sir. We
Okay, thank
Electronics
you.
Engineering Department
Thanks.
remain thankful to all the participants who joined this session to make it successful. I hope you all are benefited from this session. Once again, thank you all for your attention. Thank you.